Okay, last time we started looking at electromagnetic induction, and we're just going to jump into some practice to show you how this works. We're trying to do the efficient version of the course here online while you guys are learning from home, so let's just jump into it and see what we can do. So I'm going to start with, I'm going to draw a magnetic field, something like this. I'm going to put a coil of wire in it, okay, something like this. And let's say we've got a 0.46 Tesla magnetic field, and let's say that we've got the coil here. We need the area of it. Let's say it's 0.076 meters squared area. We've only got one loop of it, and okay, this should all be good. So let's just start with some of the basic calculations that we incorporated or started learning about last video. So let's start with this. I want to know what's the flux going through the coil. Okay, so I'm just going to start with this. Now, if you remember from flux from electric fields was EA cos theta, this is BA cos theta. So right now, the magnetic flux is BA cos theta. Now, the trick, of course, as you guys, of course, call it a trick, is the angle thing. Now, if you remember, the angle is not between the coil and the field, it's between the normal to the coil and the field. Remember, if we have there's actually a arrow that comes out here, which is called the normal. And that's where the angle is measured from. So the angle is actually between the normal and the fields, which is like right in there, which is 0 degrees. And of course, the cos of 0 degrees is 1, which makes sense because then we have maximum flux and we've maximized the cos theta relationship. Because if you look at the coil, that's set up for maximum interaction. So that's what we'd want to use. We've got the B, we got the A, we got the cos theta, and of course the cos theta is going to be equal to 1 because the angle is 0 degrees between the normal and the field. And if you're not sure which angle to use, just look at the picture. Is it maximum flux or zero flux? Well, this is maximum flux, so make cos theta equal to 1 and move on. Okay, so we've got the B, we've got the A, so all we have to do is multiply the two together. So we've got the 0.46, and we'll times that by the 0.076, and we get 0.035. Now for units, there's a couple options. B is in Teslas, that's meter squared, so you can do Tesla meter squared, or you'll often see WB, which stands for Webers, which is a really common unit for flux. Okay, so that is the flux through the coil. It's actually a really, really straightforward calculation. Okay, so now what we're going to do is let's take the situation and let's remove the coil in 0.15 seconds. So we're going to take the coil and we are going to remove the coil from the magnetic field. Okay, what is the induced EMF going to be? Okay, well, if we take it out of the coil, it's got no flux. So my magnetic flux primed, remember using prime for like means like alter or after or whatever you want to call it. If I take that coil out, there's going to be no flux through it. It's going to be 0 Webers of flux afterwards if I take it out. It's got nothing. Okay, so what I need to do is then incorporate that into my expression. So if I look at the induced EMF expression that we had last time, it was negative N change in magnetic flux divided by change in time. Well, my N value I don't have to worry about. There's one coil, so that's just 1, so I don't have to worry about that. And it's not about how much flux you have, it's about how your flux has changed. So if I started with 0.035 and now I'm down to 0, if I subtract the two, obviously my change in magnetic flux was negative 0.035 Webers. I lost 0.035 Webers. The second one, take away the first one, it dropped by that much. And that's what I want to use in my expression. So it's going to be negative times negative. So you can see those two negatives are going to cancel out. And no, you can't just drop the negatives for no reason. And we got the time of 0.015 seconds. So if I divide those two values, I will get an induced EMF of around 2.3 volts. So 2.3 volts would be induced in that coil, which can then produce an induced current. Okay, so doing this is relatively straightforward. Find one flux, find another flux, find the change in flux, divide it by time. Okay, and maybe multiply it by N if you've got more than one coil. That's pretty much it. Okay, so that's the basic idea of how this type of stuff works. So let's take the exact same thing. Let's not overcomplicate by having to do a whole new question here. Let's just take this. I'm going to shrink this down a little bit, give myself a little more room. let's take the exact same setup, okay, and just modify it a little bit. So let's start the same. So we'll start the exact same thing. We've got a flux of 0.035 Webers, and instead of removing the coil, what we're going to do is we are going to angle the coil. We are going to turn the coil 30 degrees in 0.015 seconds. Okay, so I'm going to take this coil and I'm actually going to rotate the coil at a different, so it's at a different angle. So now the coil is going to be like this. So notice it says I'm going to turn the coil 30 degrees. So it's going to be a 30-degree change from here to here. Okay, so let's do the exact same thing. What is the induced EMF for this one? Okay, well, my initial flux doesn't change. There's my first flux right there, but I need to find my new flux. So if I find my new flux, that'd be BA cos theta. My B hasn't changed, my A hasn't changed, but I need that cos theta. So what's the angle I'm going to use? Well, you may want to jump it to 30, but is it 30 or is it going to be 60? This is where you got to be a little bit careful. And if you can visualize how this changes, it is going to be the 30. But the other way to look at it is, the way I prefer to look at it, is maximum or minimum in terms of the function. If I turn this coil in at 30 degrees and it was situated like this, the way it's drawn, is that closer to maximum flux or is that closer to minimum flux? Well, it's almost vertical, it's almost maximum, so it's closer to maximum flux. Well, what's bigger, the cos of 30 or the cos of 60? Well, between the cos of 30 and the cos of 60, cos of 30 is bigger. So I'm going to use the 30 degrees in there. And if you know, some people can visualize it. If you would take that coil and you would turn it 30 degrees this way, this would go up 30 degrees this way, and the angle would be 30 degrees. Some people can visualize that really easy. I often just like to go maximum flux, minimum flux, and what is it closer to? Do I want to make it bigger or do I want to make it smaller? In this case, it's closer to maximum based on how it's situated in there, and cos of 30 is bigger than the cos of 60, so I'm going to use the cos of 30. All right, so let's keep on going then. All right, so I've got my BA cos theta, so I've got my B, that has not changed. I still got my 0.46 for that. My area has not changed, and then I'm going to multiply that by the cos of 30. And I will get a flux of 0.030 Webers. So as you can see, it didn't change much, which makes sense based on the diagram and how it's set up. All right, now I don't want the flux that I have. It's all about the change in flux. So if I look at my change in flux, oops, I want a phi there, not a B. All right, if I look at my change in flux, and it's 2 minus 1, so it's going to be the 0.03, take away the 0.035. I probably should have kept another decimal place in here, but that's okay. So it went down again, so 0.005 Webers is my change in flux. Okay, and then I can do the exact same thing I did before. Induced EMF is equal to negative change in flux divided by change in time. So that's how much my flux changed by. My negatives are going to cancel out again. There's my change in flux. I'll divide that by the exact same time that I had before. So I'll divide that by the 0.015. And I will get a voltage of around about 0.3 volts. I know it's only one sig fig, but whatever for now. So we're looking around 0.0 or 0.3 volts would be induced in that coil. Okay, so again, it's all about find one flux, find the other flux, find the difference, divide by the time, and you're good to go. Okay, all right, so there's one example right there. So let's try something else. Okay, so let's go with some coils of wire. There we go. So let's say we got some few loops of wire here, something like this. Okay, so let's say we have 60 loops of wire, so we'll incorporate some of the multiple loops type thing. We've got 60 loops of wire, and let's say we've got 0.0, oh, it's okay, we got a 6 in there, 0.068 meters squared for an area. And let's throw in a magnetic field here, so let's say it's inside of a magnetic field going through. Okay, something like this. Oops, get rid of that. So let's have a magnetic field, and we will start with a magnetic field of, let's say, 0.38 Teslas. Okay, now let's go with this. Let's see. We are going to reduce the magnetic field to 0.16 Teslas. Okay, and let's say it's done, and it actually produces, let's throw an 8. It produces 8.5 volts. Okay, so how long did it take? Okay, so let's just see what we can find here. We've got field, we've got area, we've got loops, we've got a whole bunch. We can find fluxes. So I'm going to start by finding fluxes. Okay, because if I go to my core expression, induced EMF is equal to negative change in flux divided by change in time. And we will actually be incorporating that n that we had before. That's also going to be in here. We have more than one loops. So I need to find my change in flux, and I have my induced EMF to get my time. So we'll sort of piece things together here. Let's just start by finding our fluxes. Okay, so if I find my first flux, BA cos theta, the nice thing is its maximum angle, so this is going to be equal to 1, so I don't really have to worry about it. I just have to do B times A. So if I find my first flux, I get 0.0258 Webers. Okay, now I've also got my second magnetic field, so I can find my second magnetic field, or my primed one. And again, the cos theta is going to be equal to 1, so that's easy. So I just have the 0.16, and I'll times that by the 0.068, so almost similar type of calculation. And I've got 0.0109 Webers. All right, so it's not about how much field I have, it's about how much my field changes. So if I find my change in flux, I'll just subtract the two. So I'll take my second one, subtract my first one, and my change in flux is negative 0.0149 Webers. Okay, so now I've got my change in flux. I've got this. I have my n value. I have this. Time is the only thing I don't have. Okay, so now I can sort of incorporate everything and put things together. Okay, so if I want to find my time, we'll even go to original expression. E induced EMF is negative n change in magnetic flux over time. I also have to flip those two around. So my change in T is going to be negative n change in flux over my induced EMF. Okay, so my negatives will cancel again. If they didn't, we would just drop the negative, because of course time can't be negative, and we just got to piece it all together. So we got the change in flux, negative 0.0149. I'm going to times that by the 60 loops, so I can incorporate that. Okay, so I times that by 60, and then I'll divide that by my induced EMF, which was 8.5. And I will get a time of 0. Well, I'll round off here. It's like 105, but for me anyway. So about 0.11 seconds. So that's how quickly it was, the magnetic field was changed. So there's more than one way to actually change or create induced EMF. You can change the field, you can change the angle, you can change lots of things. You can change the area and the number of loops technically. By far the most common way to do it is change an angle or change the field strength. Those are the two most common ways, but all ends up being around the same type of idea anyway. Okay, so we'll do some more practice of this as well.